Good morning, everyone. Let's begin today's lecture. I had posted the solutions for quiz 1 in the same notebook. So please keep checking the notebook every now and then. This PDF gets updated by itself. Okay, so what do I expect as an answer is what is given. Okay, if there are no questions, let's get started. So far, what we have been doing is that we have been dealing with superposition of states and have converted the information from the wave function to the density matrix. And we said that the time evolution of the density matrix is given with a Liouvelle van Neumann equation, which is given as d sigma or dt is equal to minus I by h cross, the commutator of Hamiltonian to the density matrix itself. So we said if the Hamiltonian is time independent, then the solution for such an equation is given by sigma of t is equal to exp minus iht times sigma of 0 exp iht. Last few classes, we were just looking at how does this change over a function of time. We have seen many different examples where we took different initial states and asked how does the Hamiltonian end up working out for such cases. We ended up having something called the Baker-Campbell-Hausdorff expansion, which has a commutator of commutators, and therefore we were able to group certain set of operators together because there's a cyclic dependence between ix, iy, and iz. Therefore, we always nicely got, if you started with something, what do you end up with depending upon whatever you started with and the Hamiltonian. This is what we have been doing. One thing that I would like to add here is that some textbooks might give the same relation, something of this sort, where instead of time being just t, they would give it in a range of time. If you might realize, we had just set t prime to 0. All this means is that when you have a density matrix, you started from the initial state, then you go to the next state, depending upon the perturbation, the following state. So for sigma 1, sigma 0 will be the initial state. For sigma 2, the sigma 1 will be the initial state. And for sigma 3, sigma 2 will be the initial state. We'll be trying to take a look at examples where when we have a one-dimensional NMR experiment where you started at equilibrium, which will be sigma of 0, then the pulse will be sigma of 1, the remaining portion will be sigma of 2. Meaning that for sigma 0, it will be equilibrium. Sigma of 1 will treat sigma 0 as its initial state, and sigma of 2 will require sigma 1 as its initial state. That's what this expression ends up showing for time-independent Hamiltonians. So now let's take a look at what if the Hamiltonian is time dependent. That's the question we are trying to ask right now. What if the Hamiltonian is time dependent? Okay, in such a case, what comes up to be the solution is that the density matrix could be treated with a unitary transformation where you have an initial matrix and you do a unitary transformation. What's a unitary transformation? Where U inverse equal to U dagger. There are matrices which have special properties. We did see an example of what's a symmetric matrix, what's a Hermitian matrix. This is a unitary matrix where the U inverse happens to be its U dagger. What is U dagger? U transpose complex conjugate. Okay, so when you end up doing such a transformation, we will ask what happens to the Hamiltonian. So what are we trying to ask? What if the Hamiltonian is time dependent? We are trying to give a solution, or maybe a unitary transformation would help. What is this unitary transformation? We'll take a look at a moment, but basic definition of unitary transformation is that the U inverse and its U dagger are one and the same. Let's see what is d sigma r over dt. It's going to be U sigma U inverse. What is this sigma? This is the sigma without the unitary transformation. So we are still going back to this equation. Now we are trying to say if the Hamiltonian is time dependent, then this equation will not work. So how do we deal with it? So we are trying to say what if a unitary transformation would work, and therefore how would this transformed density matrix changes as a function of time? We'll see what happens. Okay. So now this is going to be d by dt of U times sigma U inverse plus U d sigma by dt U inverse plus u sigma du inverse by dt. Right? Then let's try to ask, how do we end up changing a few things? What is E here? E is identity. Sure, you guys would agree that the identity matrix does not change as a function of time. So here we will end up exploiting the fact that therefore u inverse, which is equal to identity, will also not change as a function of time. So therefore, what will end up happening? Du by dt u inverse plus u du inverse by dt will be equal to 0. This yet again implies, I have to be careful what I take, but we will worry about that when we finish, minus du inverse by dt. Is that correct? ud inverse by dt. And what can I move across here? Let me think. Okay, fine. So this being done, okay, so we have equation 1 here, and I derived this so that we slowly see how we can end up changing these. So let me end up taking this part of the equation to the next page. So let me try to do one more small step here, where I'm going to move this and then say, why don't I write a u here with a u inverse here? Can I do that? That's basically identity again. So let me write it in a different color. Basically, what am I trying to say? I want a u here, so I do u inverse time u. So, and therefore, you have something of this sort, and then you have yet another one being present, where I have to move the last part. What is the last part? I multiply by u inverse u. That's also E multiplying by identity. So quickly, what you guys are able to understand here, this becomes sigma of R, and this becomes sigma of R. Correct? So therefore, what you have here is that this will become equal to du by dt u inverse of sigma R plus du sigma dt u inverse plus sigma R du inverse dt. Right? And what else did we do? We also said we have another relation which helps us equate these two entities, which we have in the next page. Okay, so therefore, you are able to realize one part that you have here is right here, and the other part that you have is also right there, correct? Minus u du inverse dt sigma R plus sigma R u du inverse over dt plus u d sigma over dt with a u inverse. These are the different entities that are present.
D sigma by dt is that commutator.
Hamiltonian comma sigma. So what will this end up becoming is nothing but d of Hamiltonian comma sigma. Yeah, there is an I out there. Sigma comma Hamiltonian. The minus sign goes away just because you have, generally you have d sigma over dt as minus I by h cross Hamiltonian comma sigma. If you end up negating the minus sign, then the operator swaps, right? The commutator swaps. Okay, this is what you got. And yeah, so this part is going to be equal to IU times sigma h minus h of sigma with a u inverse. So IU sigma h u inverse minus IU h sigma u inverse. And then yet again, what we can try to do, IU sigma u inverse u h u inverse multiplying by u inverse u, which is identity again, minus IU h u inverse u sigma u inverse. All that I've done is to expand the commutator and have multiply by identity again. This ends up transforming this part to be sigma R. So let's write that. I sigma R times u Hamiltonian u inverse minus I u Hamiltonian u inverse sigma R. Okay? Therefore, you end up still taking the I out. You carefully observe it's sigma R comma U inverse. If you treat this as an operator, you have A times V minus B times A. Correct? So therefore, what does this end up becoming? This ends up being sigma R, comma U inverse. Yet again, what you're able to see here as well, you're able to see AB minus BA. Correct? So let me also write that. So commutator of sigma R, comma du inverse by dt. I hope I'm not missing a minus sign somewhere. Maybe if I take the I, it will come up, right? So in both these commutators, you see sigma R is first. One would be able to take this part inside the commutator, of course, accounting for the I. Let's try to expand this. Actually, yeah, this is fine. D sigma R over dt, therefore, will be equal to, how do we take this out? Let's say I by H cross. We left H cross long back, so I'm not going to write that anymore. It's going to be sigma R, comma U inverse. If I have to take this part inside this commutator, remember there is an I. What should I multiply that with? How did this minus I come? Because this does not have an I part. So you can imagine this as a minus I square. Minus I square is plus 1. So let me write it. Minus I square. Correct? So if you end up taking I out, the minus I will come up there. Right? So far, what you guys have seen is that you started with an equation which goes d sigma over dt as I times sigma comma h. This is what you started as the Liouvelle van Neumann equation. Then what are we trying to solve here? We said if the Hamiltonian is time dependent, what happens? We said that let's see whether a unitary transformation will come to a rescue. That was our question. What is the unitary transformation? The U is the unitary transformation where the density matrix gets transformed as U sigma U inverse. And when we ended up expanding the Liouvelle van Neumann equation based on that, you see that the entire expression still remains very similar, except that the sigma has converted itself to the transformed density matrix, and the new effective Hamiltonian will be something of this sort, meaning that you have transformed the Hamiltonian also, which is not a simple U Hamiltonian. It's not a simple U Hamiltonian U inverse. It has an additional term that comes up because of the time dependence of the Hamiltonian. Did that make sense? Right? Okay, that's it. So basically, that's what we wanted to do here. And that's the same thing we are able to get done with. What do we want to say here? If you have a time dependent Hamiltonian, then it gets transformed to, let's say, HE, following the nomenclature that the textbook follows, where the transformed Hamiltonian will be U HU inverse minus IU DU inverse over dt. Basically, this becomes your new Hamiltonian. Did that make sense? Yeah, we'll try to take an example and see it. Then everything that we did in the previous classes will make sense, right? Okay. So let's take the example where you are looking at the Hamiltonian, which is omega I Iz plus an RF pulse that is applied. How does RF pulse look? Can one of you tell me? You remember that B RF was 2B1 cos omega RFT plus phi, right? This is what we started with. We had an I cap in it, which we can think of an IX type operation. And if you want to convert the B1, basically omega RF would become omega 1 cos omega RFT plus phi IX plus omega 1 sine omega 1 sine omega RFT plus phi times IX. How did I go from here to here? I want you guys to recollect what we did in the semi-classical picture, where you have this given light to be decomposed into two counter-rotating linearly polarized light, and you had an X and a Y that is associated with each one of them. Therefore, you decomposed it in the counter-rotating lights and then just used one component of it, and we ended up using the plus component of it. So similarly, of course, the plus omega 1 cos part minus omega 1 sine part doesn't interact is what we said. You can either take that for the interaction or this for the interaction. We also said what is the contribution of the other part? It's the Bloch-Siegert shift that goes as B1 divided by 2 B0 square or something. Since B0 is much more higher than B1, that's a very small term and therefore it won't contribute much. Correct? So that's the same set of arguments we are making here. Therefore, here the Hamiltonian would be omega I Iz plus omega 1 cos omega RF t plus phi Ix plus omega 1 sine omega RF t plus phi times Iy.
The B yes should be Ix or not. There should be Ix or
it will be I cap.
Yes.
Yeah, the Hamiltonian will be.
It is fine. But there should be I cap.
Okay. That's fine with me as well. Okay, so now this is the Hamiltonian. Are you guys able to understand? While the Zeeman effect is time independent, you have a time dependent perturbation that exists here. What do you mean by time dependent? You have the Hamiltonian that has a time part associated with it. So therefore, why did we do this entire endeavor of trying to transform this? Is to make you guys understand, while the Zeeman effect is time independent and you don't have to care about it, the pulse part does have a time dependence that goes with it. So therefore, what do we want to do here? We want to ask, what is the transformed Hamiltonian? How do we get the transformed Hamiltonian? That's going to be given by UHU inverse and as IU du inverse over dt. But what is U here? Because you need to know U so that you can understand what is sigma R, which will go as the initial density matrix times the U times U inverse. What do you think will be the most appropriate choice for this unitary matrix? This is close to the rotating frame transformation in the semi-classical part. You guys might remember we went to a frame of reference where the precision about B0 was negated or lost. You don't see it. Similar thing we are going to do. So therefore, you are able to realize that for U should be of the form of e power omega RF t times Iz. Basically, you're allowing for anything that happens along Z with the frequency of omega RF to be negative. We are going to the frame of reference along Z. What did we do there? We said that, okay, then the B0 becomes smaller and smaller and smaller. When you are at omega RF equal to omega naught, that vanishes. Okay, so this is a similar unitary transformation where, once again, you're going very close to the omega naught set by omega RF. That will help you negate the effects of B0. We'll try to see if we take this unitary transformation, what happens. Shall we try that? Okay. What I want you guys to do in the next couple of minutes, take this Hamiltonian and then take this unitary matrix. Let's start with one simple step. Can you guys first do what is minus I times U times du inverse over dt if U is given by this part? The question is simple. If this is your unitary transformation, can you just evaluate this aspect of it? the one simple thing that many people end up missing is that if you have e power I theta as your unitary matrix, e power minus I theta is the inverse. So don't forget that. Like, what did we say? U inverse equal to U dagger. Correct? Dagger means you take a complex conjugate. So you end up taking e power I theta, it will become e power minus I theta. You take a d by dt of, or d by d theta of I theta, you will just get I theta back up here. Correct? The minus sign comes because of the complex conjugate. So therefore, what ends up happening is that these two e power I theta and e power minus I theta become one, and you have minus I times minus omega r of I omega r of Iz, minus I square will become minus I times minus I becomes plus I square, which will be minus 1, and you end up getting minus omega r of Iz. Okay? At the same time, there is one more part left. What did we say? To transform the Hamiltonian, we have two parts of it. And this is the part we just evaluated. Correct? So let's look at the second part. Once again, pens down, please. So this part is simple U inverse that is present. And you know what is U right now. And you know what is H, the Hamiltonian. Let us take one moment and ask, if this is your Hamiltonian, remember you have omega I Iz. Do you think this part of the Hamiltonian, the Zeeman part of the Hamiltonian, will get transformed with this unitary transformation, or will it remain the same? Will there be any change following transformation? Why?
Because because Zeeman term commutes with the unitary.
That's right. Okay, so the A part consists of U inverse, and the Hamiltonian has omega I Iz plus omega 1 cos omega r of t plus phi times Ix plus omega 1 sine omega r of t plus phi Iy. We were trying to ask, will this part of the Hamiltonian transform, given that the unitary transformation has given us exp I omega r of t times Iz. And if you slowly pay attention, U inverse is nothing but exp I omega r of t Iz times this part of the Hamiltonian, which is omega I Iz, times the inverse of this. And you slowly realize all the operators have Iz in them. Basically, you're just trying to evaluate the commutator of Iz, Iz in the BCH expansion. Therefore, you can say that does not evolve. Did that make sense? So therefore, immediately what is going to happen in the transformed Hamiltonian, you're only going to have omega I Iz without any change, plus U inverse acting only on this portion. I want you guys to take another 2 minutes where you end up taking U as equal to exp I omega r of t Iz, and then just solve for each one of them. For instance, solve first for cos omega r of t plus phi Ix. Solve for something like this using this unitary transformation where you go U, you have U here. This part, as think of it as partial part of the Hamiltonian, and U inverse. Can you tell me what do you get? The Ix part. Please solve it. For this, the BCH expansion will come handy. If you end up taking the unitary transformation with the Ix part, of course, all this is constant, that is going to come out. And you just have a Z rotation for the X part. Then what did we learn? Counterclockwise rotation about the axis that is given by the Hamiltonian, e power minus IH, right? Okay, I think I made a small mistake here. Or is this right? We had a minus sign here, isn't it? And then a plus sign here. So remember, so what is going to happen? This is going to be a counterclockwise rotation. Initially what we defined. So this will be a clockwise rotation. So be careful about that. So maybe I made a small mistake. Let me see. Did that make sense on what I said? You had a e power minus IHT. Therefore, we said it's a rotation that is counterclockwise to this. If you had a minus, then this would have made sense. I'm thinking, I'm just correcting myself while I write. So I might make another mistake, but we'll see. Okay. So therefore, one could actually write this based on whatever we had seen earlier, correct? And therefore, what do we end up happening? What do we end up having here? Omega 1 cos omega r of t cos plus phi plus cos omega r of t plus sine. So what do you think this expansion will be? Let me correct it. So this is going to be with a minus. This is going to be with a plus. If you end up taking omega ix out, you have a cos of omega r of t plus phi you have a cos A cos B plus sine A sine B. This is cos of A minus B. Omega r of t plus phi minus omega r of t. So therefore, immediately you see that the omega r of gets cancelled with each other. Let me say plus omega 1 iy sine omega r of t plus phi. You have a sine A cos B minus cos A sine B. This is sine of A minus B, correct? So therefore, this is also going to be minus omega r of t. Yet again, you see the omega r of t goes away. And therefore, the net result of that is going to be omega 1 ix plus omega 1 iy. Sorry. Cos phi plus omega 1 iy sine p. How many of you understood this part? Please raise your hand. Good. Everybody in page. I'm so happy. So therefore, what? Let's see the final outcome. If you started with the Hamiltonian, which is omega iz plus omega 1 times cos omega r of t plus phi ix plus sine omega r of t plus phi iy. If you apply the unitary transformation of exp I omega r of t iz, then what is the transformed Hamiltonian? What is the transformed Hamiltonian? I'm going to write all the parts that we started with. What are the parts? We said the first part will remain as it is. Second part is what we did in evaluating right now. So let me put those two together first. This one will be omega iz plus omega 1 ix cos phi plus iy sin phi. Don't ever forget there was a third part which we evaluated to start with, which was nothing but minus omega r of iz. Correct? So therefore, what comes up? Minus omega r of iz. Now, if you look at the transformed Hamiltonian, that's nothing but omega I minus omega r of times iz plus omega 1 ix cos phi plus iy sin phi, which is nothing but capital omega I iz plus omega 1 ix cos phi plus iy sin phi. What have we effectively done is to start with a time-dependent Hamiltonian, and I've now gone to a time-independent Hamiltonian following this transformation. The advantage of this right now is that you can use this directly in the Liouvelle van Neumann equation type expansion, where you would start with d of dt over sigma of r will be given as I times sigma of r times the, commutator, the evolved Hamiltonian. If you're starting from equilibrium, you might realize that the Hamiltonian itself is the Zeeman Hamiltonian. So therefore, your unitary transformation will do literally nothing to it. It will remain as it is. Do you see that? So therefore, what you can do is to start your experiment. If you're starting from equilibrium, this is known. This has been transformed. Correct? And therefore, slowly you see that the effect of precession comes up as an offset. An effect of the pulse merely comes up as a rotation with respect to that axis. Just to recollect, in case people forgot, what is the phi? Phi is equal to 0 for an X phase pulse, phi equal to 90 degrees or pi by 2 for a Y phase pulse. Phi equal to 180 degrees for a minus X phase pulse, phi is equal to minus 90 or 270 degrees for a minus Y phase pulse. The moment you substitute those values, one or the other will exist or vanish. That might be a combination where you choose phi as 45 degrees. Let's not discuss that right now. You could do something like that. But overall, do you see that the effect of precession reduces itself to an offset, while the effect of a pulse reduces itself to mere rotations about which axis you apply the pulse? This is why for the last two classes, I was giving you guys examples of different Hamiltonians and different pulses that are applied across different axes. And just to recollect the quiz question that was given, one of the quiz question was, if you started from equilibrium, when you end up applying a pulse, where do you finish up? This is what was the quiz question, which we ended up solving quite a bit before we came. That is still in sync with what we learned. But the additional advantage that you get with the density matrix is that you'll be able to see some of the terms that you're not going to see in bulk magnetization. You don't understand where does the multiple quantum exist in the bulk magnetization. You cannot imagine it. But here, on the other hand, if you're able to get a 4x4 density matrix, you guys know which parts are double quantum coherences. Remember the 4-1 and 1-4 terms were double quantum, right? You remember the 2-3 and 3-2 terms were zero quantum. Anyway, so that is the entire purpose of what we wanted to do. And the last few classes, what you ended up doing was to use different Hamiltonians and different initial states to understand what will be the final thing that comes out. And this is how we end up also changing the time-dependent perturbation in terms of the Hamiltonian to a time-independent. That's why we never wrote omega R of t in the entire two classes last week. We just kept on writing, okay, what if it's omega 1 times Ix? And remember, omega 1 times tau p became alpha, whatever. Now let's finally try to understand the one pulse NMR experiment. We are really at the end of understanding density matrix. Now we are just going to blindly apply it left, right, and center. You'll see that most of it will happen after the midsem. But let's take a very simple example, which we have already dealt with before. So this is at equilibrium. This is the alpha degree pulse you applied. This is the FID. From here on, we'll be trying to draw pulses as rectangles, delays as nothing. So there's a simple one-dimensional NMR experiment. What is so one-dimensional about it? Can somebody tell me? Does the spectrum look one dimension? The NMR spectrum of a 1D NMR experiment is 1 dimensions or 2 dimensions or 3 dimensions? 2, right? So what is one dimension about this? So the one dimension indicates the number of axes you do Fourier transformation. Okay, it's a single dimension Fourier transformation. Time becomes omega. So that's what the dimension is right now. There is only a single time domain, and that becomes a frequency. So the 1D indicates not the dimensionality of spectrum, the dimensionality of Fourier transform, complex Fourier transform you're performing. Okay, so this is a simple one-dimensional NMR experiment where you have a delay to start with. We'll understand what this delay means and why is it required. You have a pulse and then you acquire the signal. What is the full form of FID? Yeah, what is free about it? Buy two, get one free. Yeah, free precession. Okay, and I stands for induction, that comes up, magnetic induction of the bulk magnetization that precesses and cuts a coil. Decay because there is a relaxation that's present. So from here on, I'm not going to say NMR signal, I'm going to say FID. The moment I say FID, you should get, okay, what's free about it, what's induction about it, what's a decay about it, and what are the information that comes out of it. It has a lot of information. That's the information content. And what did we do in the last 2-3 weeks of lectures? We said, okay, if I know the wave function and or the density matrix, I can tell what's going on. Now we are going to combine these two. Okay. It's very simple application. Let's take the example CH3OH. Just for the sake of it, I'm taking this example. What kind of system is this? This is something like AX3 system. Do you guys agree on that? If you put it in DMSO D6 as a solvent, what should be the multiplicity of A?
4.
4. You don't call it 4 in NMR, you call it a quartet. Can you answer what should be the multiplicity of the X spin?
Doublet.
So this is a simple AX3 system. We'll try to see how does this one-dimensional NMR work. Here, what is the density matrix at equilibrium is what we are trying to ask. So it is going to be nothing but omega proton, both are proton spins, right? Omega H, or you can actually say omega A, AZ plus omega X, XZ. Should I not use ANX? I'll use INS. S3, I. Therefore, I will be a quartet, S will be a doublet, because X and Z will get confusing. So let's say this is going to be omega I, IZ plus omega S, SZ. This is the equilibrium density matrix. Is that correct? Am I missing something? Yes, I'm missing something. I'm missing a multiplied by 3. There are 3 protons that are being present for the methyl group. Okay, this is where the integration works out in NMR, where you end up getting a spectrum. When you integrate, how are you able to say how many protons are there? That's because the density matrix goes with the number of spins that are present. Therefore, by default, with respect to a single proton, triple proton will be more in intensity of its signal because it has thrice the amount of signal that arises out of it. That's exactly why NMR is a semi-quantitative technique, isn't it? If NMR is not semi-quantitative, you will not be able to say which is CH, which is CH2, which is CH3. For people who have seen NMR spectrum, the moment people take an NMR spectrum, they look at chemicals of scalar coupling and integration for small molecules. The integration works out because of this factor. Okay. Then what comes up next is the 90-degree pulse that is applied. And remember, the 90-degree pulse that is applied, let's just take it along the Y phase, just for the sake of simplicity. And it's applied on both the spins I and S. Basically, we are trying to say it's a hard pulse. What does hard pulse translate for you guys? Let's assume that, therefore, offset is more or less 0. Offset is there, but let's say these spins are really close to each other. Therefore, your pulse, what did we mean as offset? You might remember theta will come up as tan inverse of omega 1 over small omega. If you're able to apply a much larger omega, small omega 1 or capital omega, then you can almost treat the off resonance effects to be 0. For most of the course, let's have this assumption. This is not true, but this will make your understanding easier. Okay. If you end up applying the pulse, so this is where we started. There we wrote sigma of 0. Then you applied this pulse. When you applied this pulse, what do you end up getting? Sigma of 1 will be omega I, Ix plus 3 omega S, Sx. Agree? Right? Slowly, I'm going to let go of the omega I and omega S. Just because both are protons, they're very, very close to each other. The chemical shift difference is not going to change their populations as much. It just goes to the paramagnetic ratio. For a carbon and proton, this would make sense. But a proton and proton, that's a multiplication factor. We can keep it out. So therefore, next step that is going to happen is the signal acquisition during time t. Now the question that comes up, you had the pulse. When you're applying the pulse, you said it's almost a non-resonance pulse. So you can remove the off-resonance effects that come in. Meaning that the Hamiltonian that you had, effective Hamiltonian, you're not going to worry about this part. You're only going to worry about this part. And you said this part went to 0 because you applied a 90-degree Y phase pulse. So you have only rotation along the Y. The moment you have rotation along the Y, it comes along X. So you realize that now that we learned so much derivation on how to transform the Hamiltonian. And once that is done, we can forget it. We can know for a fact that's how it looks. And we end up just directly applying it to to the fact that Z becomes X. So far, so good. Now, after the application of the pulse, what remains? Only the B0 remains. When the B0 remains, what is the Hamiltonian at this time? The Hamiltonian is going to be sum of the chemical shift and the scalar coupling, right? Where the chemical shift Hamiltonian yet again is omega I Iz. Sorry. Now we went to the rotating frame, capital omega I Iz plus capital omega S SZ. Here 3 will not come. This is a Hamiltonian. This is not based on how many spins are there. This is what is the interaction. Very simple question. Correct? And let's take for an example of weak coupling Hamiltonian, where it's going to be pi j is 2 Iz SZ. Okay? What I want you guys to do, this is very simple. We have done this several times. If you have this Hamiltonian, where scalar coupling and chemical shift for each of this, tell me what will be sigma of 2 tomorrow. Go back and please solve this. This would matter. I'm going to kind of rush through it because there's the last few minutes. So sigma of 2, therefore, will become, let's do chemical shift first. Okay, this is something that's important. You have 2 interactions that are present. Therefore, your EXP minus IHT would become EHT IH1 plus H2 times T. So basically, you have an e power A plus B kind of a relationship. E power A is equal to E power A times E power B only if commutator AB is equal to 0. Commutator AB indicates that whether A and B order can be reversed or not when you make a signal direction. The case that A, B commutes with each other, first of all, you can write it as E power A times E power B, and you can switch E power A times E power B as E power B times E power A, meaning that if A comma B is 0, then E power A plus E power B is equal to E power A times E power B, also equal to E power B times E power A. In this case, do you guys realize that the Hamiltonians commute with each other? So you can either do the chemical shift first, followed by scalar coupling, or to scalar coupling followed by chemical shift. I request you guys, now that we have slowly elevated what we are trying to do, we have done so much math, and we have agreed whatever formalism we have developed is making sense. Therefore, take this as the density matrix, apply the entire Hamiltonian, and tell me whether you understand the spectrum of methanol. Do this mathematically. You would not know what is the offset of the methyl proton, the offset of OH. Doesn't matter. Just put it as omega CH3 at one point and OH at some other point. This is just number. These are facts. These facts are determined by the electronic effects, which we cannot predict from the course. Whole idea of this course is that if I take a sample, do I understand how NMR works? Tomorrow when you guys come, I request you to tell me what is sigma of 2. As I just said, I've given you hints on first apply the chemical shift, which is easy. What is going to chemical shift be? Is going to be cos of omega I times T plus IY sine of omega I times T plus 3SX cos of omega S times T plus 3SY sine of omega S times T, followed by scalar coupling Hamiltonian. Cos of omega IT will be out, IX cos pi JT plus 2 IYSZ sine pi JT, and so on. Write all the other terms. We'll try to look at this term and see how the spectrum comes up tomorrow. Okay? Please do the matrices, 4x4 matrices for the operators as well. We'll start with these two tomorrow.